Hello everyone, welcome back. Today we are tackling another tree problem, Leetcode 105, construct binary tree from preorder and inorder traversal. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given two integer arrays, preorder and inorder, where preorder contains the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree. And our job is to use these two lists to construct and return the original binary tree. First, let's refresh what is preorder and inorder traversal. Say with the tree in example 1. Now when we perform the preorder traversal, we visit the root first and then the left subtree and finally the right subtree. So we start at the top and immediately visit 3. Next we process the entire left subtree where we land on 9 and immediately visit it. And since it doesn't have any children, the traversal on the left subtree is now complete. So we return to 3 and now process the entire right subtree, again starting with 20 as the root of the right subtree and immediately visit it. Then we go to its left subtree where we see element 15 and visit it. And finally we process its right subtree and visit element 7. And we can see that this preorder traversal matches the preorder traversal in the example. Next, in inorder traversal, we visit the left subtree first, then the root, and finally the right subtree. So here, for example, we start at the main root 3, but we can't visit it yet because the rule says we must go to the left first, where we see the leftmost child 9. And since 9 doesn't have any left child, we can visit it. And this completes the inorder traversal of the left side of the tree. And now we go back to the parent and visit it as well, as we have visited its left side, and go to its right subtree which is rooted at 20, but we can't visit 20 yet because it has a left child. So we must follow the rule again and go left to its child 15, and since 15 has no left child, we visit it and go back to the parent 20. And since left side of 20 is done, we visit it and go to its right subtree, which is last node 7, and visit it. And this completes the inorder traversal. And we can see that this inorder traversal matches the inorder traversal in example as well. I have also covered these traversals in the short videos. In case you are interested, please check out the I button or the description for more. So we see that these traversals describe the tree we need to build, but how do we actually build it? This problem might feel familiar if you have seen the related challenge of building a tree from preorder and postorder traversal, a topic we will be covering in a future video. However, there is a critical difference that when we build the tree with the preorder and postorder traversals, the tree isn't always unique, but with preorder and inorder traversal, it is guaranteed to be unique. We'll see why shortly. Now, the first clue comes from the preorder traversal. We can see that the very first element, 3, has to be the root of the entire tree, because in the preorder traversal, we visit the root node first and then the left and right subtrees. So this gives us a starting point. But what should we do next? We have the root node, but how do we place the rest of the nodes from the preorder array? Will they go to the left or to the right? And visually we can see that the element 9 goes to the left of node 3 and remaining elements, that is 20, 15 and 7, go to the right. So there is some sense of partition between 9 and 20, where left of partition goes to the left subtree and right of it goes to the right subtree. And programmatically, this is where inorder traversal will help us. Remember, the rule of the inorder traversal is that we go to the left subtree first, then the root, and then to the right subtree. So if we look at the position of root node 3 in the inorder list, we can see that it perfectly partitions the inorder array into two parts, where 9 goes to the left and the remaining nodes 15, 20 and 7 go to the right subtree. So now we have this root node 3 and we know the node on its left and right, but we still need to build these left and right subtrees. So we can look at these construction of subtrees as having two smaller independent problems, where on the left side we have the inorder subarray as 9 and on the right side we have the inorder subarray as 15, 20 and 7. We do the same for the preorder array. Since we know that the left subtree has only one node, the next element 9 is for the left subtree's recursive call, and the remaining elements 20, 15 and 7 are for the right subtree's call. So I am marking the preorder subarrays in red and inorder subarrays in yellow. And now let's solve the subproblem on the left. The preorder array tells us that root is 9, and looking at the inorder array, we see 9 has no left or right children, which means the left subtree is complete. And with that done, let's solve the subproblem on the right, where we see as per the preorder traversal, 20 is the new root. And in the inorder list, we have one element on the left of 20 and one element on the right. So this again triggers two recursive calls, passing in the preorder and inorder array as 15 on the left and 7 on the right. And both of these are simple base cases and they return the node itself, which are 15 and 7 respectively. And with its children attached, node 20 is now complete and the entire tree is built successfully. So to summarize, in the base case, if the input arrays are empty, we return null. Otherwise, we take the first element of the preorder array as the current root and scan the inorder array to find the root's index. And typically, because of the linear search, this is a slow part. And using that index, we can identify the portion on the left and the portion on the right, making two recursive calls, one for the left subtree and one for the right. Now the time complexity of this approach is O of n square, where n is number of nodes in the tree, because we make n calls for each element in the preorder traversal. And inside each of these calls, we scan the inorder array to find the current root's index, which again take O of n time, resulting in the overall time complexity of O of n square. And the space complexity will be O of h due to the recursion stack, where h is the height of the tree, which in the worst case will be O of n in case of skewed or unbalanced tree. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. In both the codes, we start the process with the recursive helper function. In Python, we can use the main build tree function itself, passing in smaller newly sliced lists with each step, while in Java, we use a separate helper function which takes in three indices: pre-start, which is the root's index in the preorder array, initially equal to 0, and instart and inend, which define the bounds for the inorder array, while we move the preorder and inorder arrays as the class attributes to keep the helper function signature clean. Now in the helper function, first thing we check is the base case, which is when there are no more nodes to process, and in this case we should return the null node. In Python, the base case is when the input becomes empty, while in Java this happens when the starting index of the inorder traversal is greater than ending index, or the starting index of the preordered array is greater than its length. Next, we identify the root of our current subtree, which is the first element in the current preorder segment. We grab its value and create a new tree node. After creating the root node, we can do a small optimization where we can check if it is a leaf node, that is, it has no children, which we can do by checking if the starting index and the ending index in the inorder array is the same. In that case, we can return the root immediately. Note that this is just an optimization. We can also skip this step in our code. And now comes the critical slow step, where we find this root's value within the inorder array to determine the boundary between the left and right subtrees using a linear scan. In Java, we have written our own linear search function, which finds the value in the given array between the start and end indices. while in Python we can use the built-in index method. Next, we make two recursive calls, one for the left and another for the right. In Python, the code is simple but inefficient, where we use slicing. First, breaking the in-order list into two parts, where everything to the left of the root becomes the in-order list for the left subtree, and everything to the right is for the right subtree. Next, we use the size of that new left in-order list to figure out how to slice the preorder array. The elements for the left are ones after the root, and the rest of the elements make up the preorder list for the right subtree. And finally, we make two recursive calls on the left and right using the new smaller sublists. While in Java, the code is slightly optimized as we are using the indices instead of making the array copies. Also, copying arrays in Java is more verbose and less syntactically elegant than Python's clean slicing notation, where for the left subtree, we pass in the pre-order index as pre-start plus 1 because now we have to pick up the next element after the current root, and the left subtree's in-order range will be from the start to the index right before the root. Similarly, for the right subtree, the in-order range will be from the index after the root to the end of the section. And for the right subtree's preorder index, we simply jump over all the nodes that belong to left subtree, which we can get by subtracting the starting in-order index from the root's index. And our starting point will be the very next element after it. And in the end, we return the root node, which will be attached to its parent after the call stack. Now, given the smaller constraints of the problem, this naive approach will be accepted. But can we do better? And the answer is yes. The most obvious bottleneck in our naive solution is the repeated O of n linear search for the roots index in the in-order array. So instead of doing the linear search, we can pre-process the in-order array into the hash map. And we can do this because in the constraints it is given that the values in the arrays are unique. Here, for example, for this in-order array, we can get the in-order map as following. And now looking up for the position of any root just takes O of 1 time. For example, when we look up for the root node 3, the map instantly tells us its position is index 1. And this confirms that there is one node on the left and 3 nodes on the right. The rest of the recursive logic stays the same. We just use map for faster lookups instead of a slow linear scan. Another bottleneck, especially pertaining to the Python code, was list slicing. Creating new copies of lists at every step of the recursion is also inefficient. So, similar to Java code, we can use indices in Python as well. By combining the hash map for lookups and indices for array boundaries, we can create a truly optimal O of n solution. However, the space complexity remains O of n as we are still using the recursion stack and now also the hash map to store in-order indices. Let's walk through our final optimal code, again with Java code on the left and Python on the right. In the main build tree function, we first do the setup, where we populate the class level variables, preorder for the preorder array, and most importantly, the in-order map, where we store each value from the Inorder traversal to its index, and it is key to our O of 1 lookup optimization. After this, now we trigger the recursive call, calling in the helper function. And again in the helper function, we take 3 indices, start index of the preorder, and the indices in start and in end, which are the range or bounds in the in-order array, which we are considering for the current recursive call. And this avoids slicing of arrays. Now inside the helper function, first we hit the base case, which is when there are no more elements to process. That is, when the starting index in the in-order array is greater than ending index. In this case, we will return null or none in Python. Next, we get the current roots value from the preorder array. using the pre-start index. And then instead of a slow linear search, we find the position of this route in the Inorder traversal using the Inorder map, which we can store in the variable, say in index. Next, we calculate the left subtree size by subtracting the starting index from roots index in the Inorder array. And this is the final piece of information we need to make the two recursive calls, where on the left, we move the index in the preorder array by 1, and the range of the Inorder array will be from start index to the index just before the root. And for the right child, we calculate the index of the preorder array by jumping over the size of the left subtree, and range of Inorder will be from the index just after the root and up till the end of the Inorder array. And finally, we return the root node, which gets passed up the call stack and attached to the parent node. So by now, you would have guessed why is a tree constructed from preorder and inorder traversal is unique, while a tree from the preorder and postorder is not. It comes down to how the root is positioned. With the preorder and postorder, we can find the root at either side of the children. So root is the first in preorder and last in postorder. But we can't tell where the left subtree ends and the right subtree begins. For example, if we are given the preorder traversal as AB and the postorder traversal as BA, we know that A is the root because it occurs first in the preorder and last in the postorder. But is B its left child or its right child? Both are possible, so we can't be sure. But with preorder and inorder traversal, there is no ambiguity. For example, if we have the inorder traversal as AB, we know that B will be the right child of A because it occurs after the root. And similarly, if the inorder traversal was BA, we know that B is left child of A because it occurs before the root. So once we find the root, the split is absolute, as there is only one way to partition the nodes. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.